Good morning, all of you. Now, let us discuss about the nested intervals and its properties. What is a nested interval? A collection of intervals. That is a collection In, where n is a natural number, that is I1, I2, etc. Having the property that I1 supersets I2 supersets etc. In supersets In plus 1 supersets etc. is called a sequence of nested intervals. It is called a sequence of nested intervals. So means In superset In plus 1 for all n fallen n, then these types of sequence of intervals are called nested intervals. Agree? Now consider In equals closed interval 0, 1 by n. In equals closed interval 0, 1 by n. Then, so what about I1? I1 equals closed interval 0, 1. I2 equals closed interval 0, 1 by 2. I3 equals closed interval 0, 1 by 3, etc. Agree? Means 0 fallen In for all n fallen n. Since it's of closed interval, 0 fallen In for all n fallen n. So the only element present in In is 0 itself. That means when In equals closed interval 0, 1 by n, then intersection n ranges from 1 to infinity In equals singleton set 0. When In equals closed interval 0, 1 by n, then 0 presents in In for all n fallen n, that is immediate from this I1, I2, I3, etc. Then we can conclude that intersection n ranges from 1 to infinity In equals singleton set 0. Agree? Now we discuss an important property, that is nested interval property. What is the nested interval property? The theorem states that for nested interval property, theorem states that let In equals closed interval a and b. Let In equals closed interval a and b. So what about the length of In? Length of In is bn minus a, where n fallen n being a nested interval, which is closed nested interval or nested sequence of closed and bounded. That In equals closed a and bn, where n fallen n be a nested sequence of closed bounded intervals. Then there exists a theta fallen r such that theta fallen I. Theta fallen r such that theta fallen I. So this is the nested interval property. So how to prove? This can be proved by using the following arguments. So it is given In equals closed a and bn, In equals closed a and bn, be a sequence of nested sequence of closed and bounded intervals. That means set of all In where n fallen n be a sequence of nested intervals. In equals closed a and bn be a sequence of closed and bounded nested intervals. Therefore, set of all In where n fallen n being a sequence of nested intervals. Then by the definition of nested intervals, we have In superset of In plus 1 for all n fallen n. That means where we have In, what is In? But In equals closed interval a and bn. So what is I1? I1 means closed interval a1, b1. Agreed. In, it is given in equals closed interval an bn. So what about I1? Closed interval a1 b1. I2 closed interval a2 b2. In closed interval an bn. In plus 1 closed interval an plus 1 bn plus 1 etc. Since in bn nested sequence, we have I1 superset of means closed interval a1 b1 superset of. I2 means closed interval a2 b2 superset of, etc. superset of, closed interval an bn superset of, closed interval an plus 1 bn plus 1 superset of, etc. and so on. So from here we can immediately conclude that a1 less than or equals a2 less than or equals a3 less than or equals etc. less than or equals an etc. less than or equals etc. less than or equals bn less than or equals etc. less than or equals b2 less than or equals b1. From this we can immediately conclude a1 less than or equals a2 less than or equals a3 less than or equals etc. less than or equals b2 less than or equals b. That means clearly it is an less than or equals b1, an less than or equals b1 for all n following n. Okay. Now, so mark it as equation 1. Now define a set. Let A equals set of all an where n is a natural number. Define A equals set of all an where n is a natural number. So an less than or equals b1 for all n following n and A equals set of all an where n following n. So from these arguments we can say that b1 be an upper bound of A. Agree? b1 is an upper bound of A. That means b1 is an upper bound of A. b1 is an upper bound of A means A is bounded above. Agree? A is bounded above. So by the completeness property or supremum property, A has a supremum. So let theta is, let supremum of A is exist. Let theta equals supremum A where theta fallen R. Theta is a real number. Theta equals supremum A. Theta equals supremum A means we have A equals set of all an. So we have an less than or equals theta for all n following n. An less than or equals theta for all n following n. Now an less than or equals b1, but here again from this one we can say that an less than or equals bn. From here also we can say that an less than or equals bn for all n. That means bn is also an upper bound of A by the construction of set A. Bn is an upper bound of A. Bn is an upper bound of A means what is theta? Theta is supremum of A. So theta less than or equals, bn less than or equals, bn upper bound of A. Therefore theta less than or equals bn for all n fallen n. So from come to this 1 and 2. This 2 gives an less than or equals theta less than or equals bn. An less than or equals theta less than or equals bn for all n fallen n. That means theta fallen closed interval an bn. What is closed interval an bn? Closed interval an bn is by the construction it is I. So theta fallen I. Agree? Okay. So this is the nested interval property. A less than or equals theta less than or equals bn means theta fallen closed interval a and bn thus theta fallen I. Enough. So this is the nested interval property. So this is an important property, nested interval property. Nested interval means sequence of nested interval is in superset of n plus 1 for all n fallen n. Okay. Now there is a theorem. The theorem states that let in equals closed a and b. Let in equals closed a and b. for all n fall in n. Be a nested sequence of bounded and closed intervals. Means set of all in where n fall in n be a nested sequence. Such that the length bn minus an of this in, what is length of in? Length of in is bn minus an. So the length of bn minus an of this in satisfies infimum of length of in, means bn minus an, where en fall in n equals 0. Then the number theta contained in in for all n fall in n is unique. Then by the nested interval theorem, the nested interval property, there exists theta fall in R such that this theta fall in where theta fall in in. Then this theta is unique. The theta is unique only when the length of this in, the infimum of length of this in, means infimum of bn minus an equals 0. Then there exists theta fall in R with such that theta fall in in, then this theta is unique. Where the theta is come from nested interval property. Okay. Yes. So how to prove this one? What about in? In equals closed interval a and bn, being a sequence of closed and nested sequence of closed and bounded intervals. So clearly set of all set in where n fall in n being a nested sequence of intervals. Be a sequence of nested intervals. So since it's a nested interval, then by nested interval property, by the previous one, there exists zeta fall in R. There exists by the nested interval property, there exists zeta fall in R such that zeta fall in in where for all n fall in n. Okay. Now we have to show that this zeta is unique. How? If possible, let eta fall in R. There exists another element, let eta fall in R such that eta fall in in also. Eta fall in in where n fall in n. Then since zeta fall in in, what is in? In is closed a and bn. This is in. This is closed a and bn. That is in. So suppose there is zeta and there is eta. Okay. So from here we can conclude that an less than or equals zeta less than or equals bn. Also an less than or equals eta less than or equals bn for all n fall in n. That's immediate from that figure. Okay. Yes. That means 0 less than or equals modulus of theta minus theta less than or equals bn minus a for all n fall in a. From this 0 less than or equals modulus of zeta minus theta less than or equals bn minus an for all n fall in a. Okay. Also we have, it is given, the condition is infimum of set of all bn minus an where n fall in n equals 0. That is the hypothesis. So that means let epsilon being positive, that epsilon is positive, then this epsilon need not be an upper bound of this set. Since infimum of bn minus an, suppose it is an, so infimum of bn minus an where n fall in n equals 0, let epsilon is positive, since it is 0, epsilon being, when epsilon is positive, so epsilon is not an upper bound of this set. Epsilon is not an upper bound of set means there exists a natural number m such that bm minus am, that means natural number m such that bm minus am strictly less than epsilon. Since epsilon being not an upper bound, so there exists a natural number m such that bm minus am strictly less than epsilon. So we have 0 less than or equals theta modulus of theta minus theta less than or equals bn minus an mark it as 1 and bm minus am strictly less than epsilon mark it as 2. So combines what you get 0 less than or equals modulus of theta minus theta less than or equals bn minus an strictly less than epsilon. So strictly less than epsilon, since epsilon being arbitrary, or we can again that means 0 less than or equals modulus of theta minus theta strictly less than epsilon. Since epsilon being arbitrary, we have theta equals some eta, so the uniqueness is preserved. Okay, when a sequence satisfies nested property, then there exists a unique theta fallen R such that theta fallen in whenever the infimum of length of that interval in should be 0. Agree? Okay. Now, so this is done. Now, by using these arguments, let in equals closed interval 0 1 by in equals closed interval 0 1 by n. Then we prove that intersection n ranges from 1 to infinity in equals singleton set of 0. Okay. How to prove this in equals closed to 0 1 by n or intersection n ranges from 1 to infinity in is singleton set to 0 by using this Archimedean property. We can prove it by using some reasonings. I1 equals close to 0 1, I2 equals close to 0 1 by 2 0 in. Sorry, 0 1 by n means I2 equals 0 1 by 2, I3 equals close to 0 1 by 3. So 0 is the only element in in. So intersection n ranges from 1 to infinity in equals singleton set to 0. Otherwise, how to prove this one? The other method is by the definition of in. So we have 0 fallen in for all n fallen in. Okay, I1, I2, etc. and so on. So 0 fallen in for all n fallen in. So it gives means 0 equals 0 fallen intersection in, where n ranges from 1 to infinity for all n fallen in. Enough. Okay. Then since in contains, so in contains only contains only non-negative number. In equals close to 0 1 by n. It does not contain a negative number, means in contains only non-negative number for all n fallen in. Then we see that since in contains only non-negative number, so we see that intersection n ranges from 1 to infinity in contains only non-negative number for all n fallen in. Given x positive, then by the corollary of Archimedean property, there exists some nx fallen n such that 0 less than 1 by nx strictly less than x, 0 less than 1 by nt strictly less than t. In that result, 0 less than 1 by nx less than x. So that means x is outside of inx, etc. So x is outside of intersection I. X is outside of inx and therefore x is outside of I, intersection I. X is outside of intersection in and ranges from 1 to infinity intersection in. So intersection in does not, x is outside of intersection in, 0 less than 1 by nx less than x, but x is outside of intersection in means intersection in does not contains any positive real number. Here we say that intersection in contains no negative real number. Here we say that intersection in contains no positive real number. Then there is by trichotomy property, then there is only possibility intersection n ranges from 1 to infinity in contains only an element singleton set of 0. So intersection for only an element 0, that means intersection n ranges from 1 to infinity in equals singleton set of 0. Okay. Now suppose this in equals open interval 0. Suppose consider as Jn equals open interval 0 1 by n. Then prove that for all n following n, then intersection n ranges from 1 to infinity Jn is empty. It's an empty set. If it is closed, it is singleton set 0. If it is open, it is an empty set. How? So it is again from the definition of Jn. We have 0 from the definition of Jn. What is J1? Open interval 0, 1. What is means J1? Open interval 0, 1. J2 open interval 0, 1 by 2. J3 open interval 0, 1 by 3. Clearly 0 is outside of Jn for all n fallen n. 0 is outside of Jn for all n fallen n. 0 is outside of Jn for all n fallen n means 0 is outside of intersection n ranges from 1 to infinity j. 0 is outside of intersection ranges from 1 to infinity j. That means now, but what about intersection n ranges from 1 to infinity jn? That is a part of J1. Intersection ranges from 1 to infinity Jn is a part of J1. What is J1? J1 is open interval 0, 1. Okay. Now we have intersection Jn does not contains any negative number. According to the construction of Jn, intersection Jn contains no negative real number. No negative reals. Intersection Jn contains no negative reals. Now again by the corollary of Archimedean property, there exists for then x is positive. When x is positive, there exists nx fallen n such that 0 less than 1 by nx strictly less than x. 1 by nx strictly less than x. So that means this x is outside of jnx. Okay. X is outside of jnx means x is outside of intersection n ranges from 1 to infinity j. So means intersection n ranges from 1 to infinity jn contains no positive reals. X is positive. So intersection Jn does not contains no negative real number. Intersection Jn does not contains no positive real number. And according to the construction of Jn, 0 is also outside of Jn means intersection Jn. So from these three arguments, we can say that intersection n ranges from 1 to infinity Jn is always empty. There is no element in this Jn. Okay. So no element lies in this intersection J. Since 0 is outside, there is no negative real number by the construction. Then by the property of Archimedean, then the